Hello everybody, welcome back to my channel Mathematics Learning with Dr. Aniruddha Palit. In the last lecture, we discussed about the uniform continuity and the non-uniform continuity criteria with their geometric interpretation. And in this lecture, we are going to discuss an important proof of the theorem that we discussed in our last lecture. And the theorem is that a real valued continuous function defined on a bounded and closed interval is uniformly continuous. So in this lecture, we are going to prove the theorem, and we shall prove an interesting example over here that 1 by x, this function, is not uniformly continuous. সো এই ভিডিওটা যদি ভালো লেগে থাকে তাহলে প্লিজ ভিডিওটাকে লাইক করো এবং আমার এই চ্যানেলটাকে সাবস্ক্রাইব করো। যদি মনে হয় যে এই লেকচারের মধ্যে যা ইনফরমেশন আছে তা বন্ধুদের উপকারে লাগবে তাহলে প্লিজ এই ভিডিওটাকে বন্ধুদের সাথে শেয়ার করো এবং আমি সকলকে রিকোয়েস্ট করব যে এই ভিডিওটা পুরো দেখার জন্য, কারণ এখানে যে থিওরেমটা আমরা প্রুফ করবার চেষ্টা করছি সেই থিওরেমটা খুব ইম্পর্টেন্ট থিওরেম হিসেবে কনসিডার করা হয়। তাছাড়া যে এক্সাম্পলটা কনসিডার করব সেটা একটা স্ট্যান্ডার্ড এক্সাম্পল অফ নন ইউনিফর্মলি কন্টিনিউয়াস ফাংশন। সো উইদাউট লুজিং টাইম, let's start the lecture number 16 from the chapter of limit and continuity in real analysis. In the last lecture, we discussed this theorem, the statement of this theorem. A real valued continuous function defined on a bounded and closed interval is uniformly continuous. Here the domain of definition would be a bounded and closed interval. We are going to prove that if a continuous function is defined on a bounded and closed interval, then it is uniformly continuous. So over here we assume that the function f is continuous on this bounded and closed interval I, and we suppose that I is equal to the interval AB, this bounded and closed interval. Okay, we have to prove that the function f is uniformly continuous on this interval I. So at first we suppose that if possible, we suppose that f is not uniformly continuous. If possible, we suppose that this function f is not uniformly continuous on the interval I. Then by the non-uniformity criteria, we can say that there exists a positive number epsilon 0, suitable positive number epsilon 0 is there, such that for any delta greater than 0, this expression, that modulus of x minus y less than delta, this expression is always satisfied. But this expression, that modulus of fx minus fy, this would not be less than any epsilon, or you can say that this would be greater than or is equal to epsilon 0 for suitable epsilon 0. And that result, all these results should hold for all xy belonging to the interval AB. Now we take that delta is equal to 1 by n. What is n? N is a positive integer or a natural number. So we take delta is equal, for n is equal to 1, we take delta is equal to 1 by 1. For n is equal to 2, we take delta is equal to 1 by 2. For n is equal to 3, we take delta is equal to 1 by 3, and so on, because this result should be true for any delta. So delta can be arbitrarily considered as per our convenience. So we take delta is equal to 1 by n over here, where n is a natural number. Then for each and every such choice of this natural number small n, we get two numbers. One is xn and another is yn. Xn and another is yn from this interval AB. Okay, so we get two numbers. One is xn, another is yn from this interval AB, such that modulus of xn minus yn is less than 1 by n. But this difference, this modulus of f of xn minus f of yn is greater than is equal to epsilon 0. So xn and yn must satisfy this condition, equation number 1, and that's why we get this result. and this is true for all n belonging to this natural number n. Okay, set of natural numbers n. So we get this second result, and now what we have, that we have two sequences. One sequence is this sequence xn, and another sequence is this sequence yn. Both of these two sequences are actually the elements taken from this interval I, or the closed interval AB. Now over here, this sequence, the first sequence, let us start with this first sequence x of n. This first sequence, both of these two sequences are actually members of the element of this bounded and closed interval AB, and so both of these two sequences are bounded and closed. Now we apply Bolzano-Weierstrass theorem for sequences. We apply Bolzano-Weierstrass theorem for sequences on this sequence xn. As because this is a bounded and closed sequence, we apply Bolzano-Weierstrass theorem on this first sequence xn, and we will get a convergent subsequence x of nk. So this x of nk would be a convergent subsequence. As because it is a convergent subsequence, it's a convergent quantity, therefore the limit of that subsequence must exist. Let us call it xi. Let xi be the limit of this subsequence. Okay, and corresponding to the elements of this subsequence from the first sequence, there are corresponding elements ynk from the second sequence. Corresponding to each xnk, there must exist ynk, because over here xn and yn, they arise pairwise. That means for each xnk there exists ynk. So these are pairwise elements, and that's why we can say that corresponding to each xnk there exists element ynk, which would ultimately constitute a subsequence ynk of the second sequence yn. We shall first prove that this second subsequence is also converging to the limit xi. So that is the first result we are going to prove, that this second subsequence would converge to the element xi. From this relation number 1, if we put x is equal to xnk and y is equal to ynk, for delta is equal to 1 by nk. Okay, we will get this result, that modulus of xnk minus ynk is less than 1 by nk, but modulus of f of xnk minus f of ynk is greater than or is equal to epsilon 0 for all k belonging to the natural number n. Okay, and therefore we can say that this difference, our target is to show that ynk converges to xi. Therefore we start with this difference, that ynk minus this xi, this difference can be written in this fashion. Over here what we are doing, we are subtracting x of nk and then adjusting x of nk. So we ultimately get this kind of result. This is in the form of modulus of a minus b. So modulus of a minus b is less than is equal to modulus of a plus modulus of b. And this ynk minus xnk, this is less than 1 by n to the power of k. And this second term remains the same. So from this relation number 2 we get that, from this relation number 4 we get that this difference ynk minus xi, that is less than this 1 by nk plus modulus of xi minus nk. As because we know that for any subsequence nk diverges to infinity as k tends to infinity. In fact, nk, these are all monotone increasing. For higher value of k, the value of nk increases. Anyway, so over here we can say that as as k tends to infinity, over here nk tends to infinity, and so 1 by nk should tend to 0. Again, as k tends to infinity, we have that xi nk converts to this xnk would converts to xi, and therefore we can say that as k tends to infinity, this difference should also tend to 0. Therefore, in any case, we can say that this right hand side would ultimately tend to 0 as k tends to infinity. And so we can say that xi is equal to limit k tending to infinity y and k. This limit xi, that means we can say that this y and k minus xi tending to 0, that means xi is actually converging to the limit, y and k is converging to the limit xi. Therefore, we can say that this xi is equal to limit of y and k. So what we have proved that that can be ultimately represented by this picture. Over here, we observe that this xnk has a this xn has a subsequence xnk, and this yn has a corresponding subsequence ynk. And this xn and yn, they ultimately satisfy this relation, and by putting n is equal to nk in this relation, we get this second relation. We already have the result that xnk converges to xi, and from this result we have proved that ynk is also converging to xi. So this much we have proved. Therefore, we can say that both of these two subsequences are converging to the same limit xi. Okay, now we are going to prove a contradiction because of our assumption. What did we assume? We assume that the function f is not uniformly continuous. Over here, each and every x and k are chosen from the interval ab. So over here, x and k should be greater than is equal to a, and that's why this limit xi should be greater than is equal to a. Similarly, x and k is less than is equal to b. Therefore, this limit xi should be less than is equal to b. Therefore, we can say that xi is greater than is equal to a and less than is equal to b. Or in other words, we can say that xi belongs to the closed interval ab. As because f is continuous in the interval ab, therefore we can say that the function should also be continuous at that particular point xi. Okay. And so from the definition of continuity in terms of limit, we can say that over here x and k converges to xi as k tends to infinity, and this implies the corresponding functional values f of x and k must converge to f of xi as k tends to infinity. Similarly, this y and k converges to xi as k tends to infinity, and this implies that f of y and k should converge to f of xi as k tends to infinity. And therefore, we can say that this limit, this modulus, is actually a continuous function. So we can interchange the position of modulus and limit. Therefore, we can say that modulus of f of nk minus f of yk, its limit should be equal to modulus of limit k tending to infinity f of nk minus limit k tending to infinity of f of yk, this expression. Now, what is this? F of this f is a continuous function. Therefore, we can again interchange the position of limit and the position of the function f. Therefore, we can ultimately write this expression of limit inside this bracket, and so this becomes is equal to f of limit k tending to infinity x n k minus f of limit k tending to infinity y n k, and therefore x n k over here, as because what is x and k? X and k is converging to xi, and therefore we have proved that f of y and k converges to f of xi. So what we have that this expression, this limit is actually beta. Therefore, this is our f of beta. This should be our f of xi, not beta. This should be our f of xi, and this should also be our f of xi. So over here, f of xi minus f of xi becomes is equal to 0. So what we have observed? We observed that limit k tending to infinity f of x n k minus f of y n k is actually converging to 0. But over here this is not possible. This is a contradiction. What is the contradiction? Because we assume that as per our assumption that modulus of f of x n k minus f of y n k, this is greater than is equal to epsilon 0 for all k belonging to the set of natural numbers n. So if this difference is greater than is equal to 0, then it can never converge to the value 0. But we have already proved that this limit is actually converging to 0. And so this is a contradiction. What for did we obtain this contradiction? Because of our wrong assumption. What was our assumption? Our assumption was this one, that f of x and k minus f of y and k is greater than is equal to epsilon 0, or in other words, our assumption was that the function is not uniformly continuous. So we can say that our assumption was wrong, and from this we can conclude that the function f is uniformly continuous on the interval a. So this completes the proof of this theorem. Now, in order to finish this lecture, we are going to discuss this example. Over here, we get a result along with one more example of the fact that 1 by x is not uniformly continuous in the interval. So we are considering the interval 0, 1. Okay, so at the first we are saying, this example says that if this sequence xn, is a Cauchy sequence in a set S. S is actually a subset of the set of real numbers R, and f is a function defined on the same set, and it's a uniformly continuous function. Then we have to show that this f of xn, this functional value, the second sequence f of xn, is a Cauchy sequence in R. And from this result, we have to show that this function a from 0, 1, open interval 0, 1 to the set of real numbers R is not uniformly continuous. So let's prove the first part first. We are given that f is a uniformly continuous function defined on the set capital S. So from the definition of uniform continuity, we can say that for each epsilon greater than 0, there exists a delta, and delta should be dependent only on epsilon. There exists a delta greater than 0 such that modulus of fx minus fy, this modulus is less than epsilon for modulus of x minus y less than delta, and xy belongs to the set capital S. So we can say that modulus of f of xy minus f of x minus f of y, this difference is less than epsilon for xy less than delta and xy belonging to the set capital S. Now we are given that this sequence xn is a Cauchy sequence in the set capital S. As because it's a Cauchy sequence in the set capital S, so from the definition of Cauchy sequence, we can say that for this given delta, for this delta greater than 0, there exists a natural number n0, and of course that natural number would ultimately depend on delta, and so we can say that there exists a natural number n0. N0 should belong to the set of natural numbers such that modulus of xn minus xm, both of this difference is less than delta for m and n greater than n0. And so we can now put x is equal to xm, x is equal to xn, and y is equal to xm in relation number 1. So if we put these results in relation number 1, then what we have, modulus of f of xn minus f of xm would be less than epsilon for modulus of xn minus xm less than delta. Okay. Now we combine this relation number 2 and relation number 3. From this relation number 3, what we can say that this first relation is true whenever this second relation or this is the same relation, this and this relation. So whenever this second relation is true, and if this second relation is true, this is true only when m n greater than in 0. So we can now combine and we can say that the first relation is true whenever m and n is both are greater than n0. So this is the result, that modulus of f of xn minus f of xm is less than epsilon or mn greater than n0. So what we obtain from this epsilon, we get a natural number n0 such that f of xn minus f of xm is less than epsilon for mn greater than n0, and this is the definition of Cauchy sequence. So we can say that this sequence f of xn, this sequence is a Cauchy sequence in the set of real numbers R. Next, in the second part, we are going to show that this f of xn is equal to 1 by x is not uniformly continuous. So in order to prove this result, we suppose that xn is equal to 1 by n. F of x is equal to 1 by x, and therefore f of xn is equal to 1 by xn. We put x is equal to xn in the relation of fx. So f of xn is equal to 1 by xn, and as because xn is taken as 1 by n, so 1 by xn should be is equal to n. So we can say that f of xn is equal to the value n. Now what we observe over here, that modulus of xn minus xm, this difference is equal to 1 by n minus 1 by m, and as m and n tending to infinity, we can say that both of these difference, both of these quantities would ultimately tend to infinity, therefore the difference would ultimately tend to infinity. So we can say that for any epsilon greater than 0, there exists a sufficiently large number n0 such that this difference is ultimately smaller than any small number epsilon for m and n, these two quantities for m and n greater than sufficiently large number n0, and so it shows that this xn, this sequence xn, this sequence is a Cauchy sequence. Next, we are going to show that the corresponding sequence of functional values, this expression, this f of xn is equal to m, this is not a Cauchy sequence. How to show this result? We find the difference f of xn minus f of xm whenever m and n are two different positive integers. So over here, f of xn is equal to this value n, and f of xm is equal to m. And therefore this difference, when m and n are two different positive integers, therefore this difference would always be greater than or is equal to 0, because of the fact that m and n are distinct. So we can say that this difference f of xn minus f of xm is not less than any arbitrary epsilon for any epsilon greater than 0, and this result should be true whenever m and n are greater than n0. So what we observe is that these functional values do not form a Cauchy sequence. So we can say that these functional values do not form a Cauchy sequence in the set of real numbers R. However, in the first part, we proved that if the function is a uniformly continuous function, then this second sequence must be a Cauchy sequence. So from this result, we can say that the function f is not uniformly continuous, because if by chance it becomes a continuous function, then this second sequence must be a Cauchy sequence. But over here we have proved that this second sequence is not a Cauchy sequence at all. Therefore, from this kind of result, we can prove that we can conclude that the function is not uniformly continuous. The function f is not uniformly continuous in the interval 0, 1. So that's all from this lecture. In this lecture, we have discussed the two important part. The first result is that the function f defined on a bounded and closed interval is uniformly continuous, and secondly, we discussed an example that f of x is equal to 1 by x is not uniformly continuous in the interval 0 less than x less than 1. So that's all from this lecture. If you think that this lecture is useful to you, please like the lecture and subscribe my channel. And if you feel that the content of this lecture would be helpful for your friends and all, so please in that case please share with them. And in the next lecture we shall discuss a little bit about the continuity of inverse function. So that's all for today. So I should finish right now. Thank you for watching this lecture. Good night. Take care.